So, is that okay? The mic is working? Yes. Okay. So first of all, my name is Elena, as you heard, and I'm an associate professor at Leiden Observatory in the Netherlands. When I start a course, even if it's a short course, usually I ask the students to write down some piece of information on a paper for me. They name how they want them to be addressed, the interests, and so on and so forth. But yesterday I didn't have the chance, so I'm not doing this. But I'm asking you, I'm hoping it will be a very interactive class. So I'm asking to tell me your name when you ask a question, or when you come up, do some exercise with me, so that then I can remember. I already know some of you. And first of all, thanks to who sent the picture of Jack Hills?
Well, I got this while you were giving the colloquium. Then the guy sitting next to me, Nadav Katz.
Nadav, yes, Nadav sent me the picture.
So I got a better one.
Ah, okay. So next time for my colloquium, I can use this one. Thank you. This is Jack Hills. Yeah. And it looks like the 70s from the mustaches and hairstyle. Who's the guy behind? Well, I don't know. Hiding behind something. Okay, so I'll just a quick poll. Who is working on tidal disruption events? Raise the hands. 1, 2. Okay. So the minority. Good. So the way I want to go about is, let's see if it works. So it's a series of questions. And so you will actually make yourself 3 exercises. And instead we will answer the other exercises together. We will make them together. If we don't know the answer, there is plenty of people that can help us. So I think we can do it. And the rationale is that I believe that these are very simple calculations. Most of the things I'm going to show I showed yesterday, but we didn't go into details. Yesterday was very shallow. And so if today we go into details and you calculate things yourself, hopefully something will stick. And you will bring home some of these notions better. Okay, so we'll start immediately by working. And so what I'm asking is for you to show. So I'm gonna do all these phases. So we start from here. The star approaching. It's at its tidal radius, and as you heard me saying yesterday, he acquires a spread. So the matter within the star acquires a spread in orbital energy equal to G m black hole over R tidal square times R star. R star is the size of the star. So the first question is. Can you derive this? And just because it's the way I like to think about it, I would like to derive it in terms of work done by a force over a length. Okay, so what is the force? Who's doing work here, against what, and over which length. And then the second question is how it compares with the binding energy of the star. How the spread compares with the binding energy of the star. Okay, so I'll give you 7 minutes, and then I have a bell. I just found it here. I thought it was funny. Okay. So please, and then I would like you to work in pairs. I think it's more fun if you want. You can ask question, okay? You're not allowed to to help. North Sea. No, you can do. You can do.
With you.
With me?
Yeah.
Okay. Okay. In the next one, yes, please. Okay, and you can ask question, okay?
So I guess you calculate it for one side and for the other side. So there's a difference in R.
You got an advantage. If you have questions, you can just ask me while I'll come around.
Can you tell what is in this?
Yes. So this is the tidal radius. And maybe you need to know what the tidal radius is to answer this question, or also this one. Okay, the tidal radius. So if you don't know, you ask me. Oh, there is a typo, actually. Is there a typo?
Right.
No, that's fine. It's not a typo. It's okay.
So the energy would have been. The energy would have been just. Energy is just. Yeah, energy per unit mass. Yeah. So then Instead of dV, I call it delta. Yeah, it's the same thing. You could say
Okay, 1 minute.
delta R is the size of the star.
Okay, let me do it. I love it. Okay, so who wants to start? Who was closer? Who feels confident? Someone solved the thing? Or knows how to start?
This is the energy per mass, right?
Yes, a specific energy. A specific energy, yes. This is to a specific energy. That's right. Yes. Nobody feels comfortable starting the discussion. So, yeah.
We think
What's your name? Sorry?
Natalie.
Natalie.
We did it as a group, so I'm giving them most of the credit. That's talk.
Yeah, you want to come over so that you can write things on the blackboard, otherwise I need to interpret. We can do it together. So, Natalie et al.
Okay, so you asked us to look at terms of work. So the force per unit of mass, so it's the gravitational force that the black hole puts on an element of mass on the star at the radius of the, like, tidal radius. I think that's what we've done. So we wrote it, that's like dF, and that's per unit mass, per unit of length as well. So we wrote it as G and black hole and the radius of the star. And then we assumed that this is larger than our star, so we can say it's fixed. And then if you wanted to go, I'm not sure that it's
That's okay.
If you wanted to go for the entire energy, then we did, like, we're looking from one edge of the star like to the other. So we're summing on the entire radius, or whatever we set at 0 to our star. Okay, and that's like dl or dr. That would be better. And then that's what we got.
And, okay.
And that's the first.
Okay. So,
What did you
okay.
What
Yeah.
did we do?
No, it's. I was thinking that there's. I want to break this down. So, what is the? So, in the star, in the star here.
Okay.
If I want to write just like f times length, with a single length and a typical length and the force, which is the force that is doing the job. Here, you wrote it, but if I want to write it like this, not differentially, but globally.
Okay, so it's the gravitational force of the black hole that's working like on an element of mass of the star, right?
So if it's a, if it's a point mass going around the black hole, it doesn't change its energy, right? So the gravitational force that doesn't do any work on the point mass, right? Because the energy in the central potential is constant. Okay, so there is so it's the finite size of the star that makes a difference, right? So what is pulling the star apart? This is the gravitational force at the center of mass of the star, but there is
its own self-gravity.
There is also the self-gravity. Yeah, I like more to think about in terms of self-gravity. I'll come back to that. But there is across the star, there is a gradient, right? So, but it's very good. So,
It's mostly like
no, not.
with Natalie and mostly like the partners.
And okay. So let me explain in my way, and then see if you like it. Okay, so this is black hole. This is the star. This is the center of mass that suffers this force. Okay, but there is a gradient. This part is pulled with a bigger force than this part because it's farther away, and the force scales with r squared, right? And so if I subtract the force in the middle, which is this one, what do I get? So this minus this is still going this way. This minus this is going the opposite. This is smaller. Let me make it smaller. It's going this way. So it's stretched. These are tides. These are the tide. First order, the tides. This is what causes the tides in water due to the moon on the earth. Okay. But the star doesn't want to give up its integrity. So the self-gravity is working hard to adjust and keep the hydrostatic equilibrium. So the way I think is that the self-gravity of the star is working hard over a length equal to the tidal radius. And this creates like work delta E. Then Rem yesterday derived the tidal radius. Remember how? Remember how the tidal radius? I wonder, eraser. Where is it? How did you?
Maybe behind the.
On the podium. Okay, here. Yeah, that's right. Okay. And then I remember then the tidal radius is the radius at which the self-gravity, the force, is equal, again, the tidal force. So it's Gm black hole. How do I write the tidal force? Tidal radius. I need a square, yes. But it's a first order, so I need R star, great, R star over RT. Okay, then I rearrange, and I find that R tidal is R star multiplied by mass of the black hole divided by mass of the star to the 1/3. If this is 1 million, this is 100, and then what is shown, the tidal radius is 100 times the size of the star. And if I put it in here, I obtain the results.
Wait, there is something wrong. It should be RT squared. Delta E expression doesn't.
If you plug, okay, I'll do the, if you plug this in and rearrange the term, force times length, self-gravity times tidal radius. We just derived the tidal radius. You plug in it and you find this. You can show by yourself. You can do it by yourself. Second question. If you take delta E and you write it like this, you have already the answer is, okay. I'm not using the blackboard very nicely today. Sorry. Okay. I don't like this. Okay. Let me do this. G m star r star square times RT. Okay, this I can write it as G m star r stars r tidal divided by r star. That's right. I'm just bringing this here. Is that right? Okay. So this is the self-gravity. Okay. This is delta E. So delta E divided by self-gravity is r tidal over r star, which we know is the mass ratio of the black hole mass divided by mass of the star to the 1/3. And so what we obtain is that delta E is 100 times larger than the self-gravity. Okay. So the spreading energy is really overwhelming with respect to the self-gravity of the star. Okay. Second, yes?
Maybe draw what force F or what force does the distance of RT seems to be. There isn't such a force. I mean, who ran through a distance of RT?
Okay. Let me do it again. Okay, that's very important because if we don't... so, at R tidal, the self-gravity is equal to the tidal force. Okay? And the self-gravity is trying to maintain the integrity of the star. Okay. So, again, so this is the black hole. This is the star with the finer size. Okay. So this is the center of mass. And this is Gm black hole over R tidal square. Okay? It's pulling towards. So here I have Gm black hole R tidal minus R star half. Right. This is R tidal for me.
Yeah,
And this is, oh, that's
just the radius.
just the radius. And this is square. Okay. And so it's bigger. Okay. This here is the opposite with the plus. So the force is smaller by this amount. Okay. If I then, I can say I put myself in the rest frame of the star, and I subtract this out of this, And out of this GM black hole, our tidal plus our star square, what do I find? So this one is bigger than this. And so I will have a force pulling still towards the black hole. This one is smaller than this, so I will have a force pulling in the opposite direction. So the star feels like stretched in the plane, at least in the plane, stretched. And what is trying to counteract that? Self-gravity. And so let me cancel unnecessary things here. So these are the tides. And this is his self-gravity. Okay. So you have self-gravity pulling and pulling in and tides pulling out. And this is what causes the arrangement of energy within the star. A question for you. What happens at the pole? What's your name? Itai. Bo.
So the forces, the direct forces from the black holes act in this angle, so you'll always have this component pointing towards the center of the star. So overall, it compresses.
Yeah. So if you subtract this over here, you have this residual component, which is compressing. Very good. So Itai taught us that in the vertical direction, the star will be compressed. And I told you that in the plane, the star will be stretched. Okay, so then we'll have an exercise on compression. Let's compress. But first, I think I have a few remarks.
So I think the delta expression is still wrong. In the first expression that you said, force into length, the force should be from the black hole, not from the star.
There are two ways to think about it.
Yeah.
You can think about individual particles going around the black hole. It's going to conserve its energy, right? So the force of the black hole
Doesn't do any work.
doesn't do any work because you include that with the potential energy around the black hole. So if you have a particle going around the black hole, its energy is conserved. And now you can think about the energy of that particle being changed by the work done by another particle on it. So you think of the two separate parts of the star as two individual particles going around the black hole. Without the forces between them, each one of them will have a conserved energy. So now the change in energy is just the force between them times the distance for which this force has acted.
So you can,
That's the way she wants to think about it by...
but you can do it in both ways because the tidal radius, the two forces are equal. So you can write G M star R stars times RT, or you can write square, sorry, the force, which is what I was mentioning, saying that you go around. But also you can use the tidal force over the length of the star, and you obtain the same result. Okay, the tidal radius are equal, so. Okay. This is on. Okay, so just a few remarks. Is that okay now? Just a few remarks. Delta E that we calculated was approximate. And it can be larger because of a compression pericenter. And we are going to calculate by how much. But also because we worked everything in Newtonian gravity. But if you add relativity, which is important for deep penetrating encounter, then the tidal force is stronger. So delta E also in simulation is found to be larger. Okay. Exercise time. Now I'll give you 10 minutes. Okay. We can do it. It's slightly more complicated, but not much. Okay. We were here, the tidal radius now I'm looking at an event that have pericenter smaller than the tidal radius. Okay, and the I taught us that as the star goes through the tidal radius, get compressed. Maximum compression is the pericenter. So as the star moves, or the debris of the star moves within the tidal radius, by definition, they are moving just ballistically, following the force of the black hole. So the star is confined within a plane, right, which intersect near pericenter. And the plane has an angle alpha. As the star moves, is compressed, and the two planes intersect near pericenter. So at pericenter, there is maximum compression, okay? And there is a compression energy associated at the expense of the orbital energy. So I'm asking, what is the compression energy at pericenter? You can think of it as the compression velocity square. So again, the star is confined within two planes inclined by an angle alpha that intersect the pericenter, and the star, as it propagates, is compressed. And there is some velocity component in this direction that give rise to the compression energy that is taken at the expense of the orbital energy of the star. So can you derive this? And then once you have this, compare again with the self-gravity of the star and with the previous delta E that we calculated. And then what is the increase of temperature within the star as it gets compressed? Oh. Okay, so let's start. And ask questions. Also to Rem, it's okay. Utsvi. Yeah.
Sorry, could you explain this gray box and the angle you were talking about? What is that?
Okay.
Or the gray.
Yeah, just a second. I'm Okay, so maybe this is the trickiest part, what you ask, but I guess, yeah, we can do it together if you want. So I guess you are asking, so you see this is a plane, an inclined plane, right, that confines the star. And this is the angle between the two planes that confines the star. Okay. The first things you need to do is to work out alpha. What is alpha? And then find the component of the orbital velocity at pericenter, which is vertical. So first, what is alpha? And this is the true anomaly at pericenter. The tidal radius, I'm sorry. So, what is alpha? First. It's just geometry. I put here everything you need. So, this is RT sine the true anomaly. And then you have the size of the star. Distance and the star. And this is the angle. Okay. Alpha. This is the star with a size R star. And this length is RT sine the true anomaly. So what is alpha? What's your name? Emanuele, come. Vieni. Bye bye. So alpha is. We are working in a small angle approximation because it's very deeply penetrating. Yeah, that's it. But then I gave you another clue that the star is moving on a parabolic orbit. So I gave you that the cosine of the true anomaly goes in like this.
So I may try to work out the
Yeah.
sign from that.
Exactly. Do you want to do it straight away? Yes. Go ahead. Yes, yes. What would you use? Some trigonometric identity, right? Yes. You see Italian universities. We do that. Teach them well.
No, I was thinking if there is something small here.
Yes, it's small because it's highly penetrating. This is a small number.
So P over RT is much smaller than 1. Okay, so it is 4 minus.
You expand.
Yeah, expanding. So I take 1 minus 4.
You can do it meanwhile, okay? Actually, please do it meanwhile. Let's see who gets first.
So I get 2 square root of that.
Okay, so what is, I want, so, yep.
Right? And then I plug in here. Sinus is 1 over 2.
Yeah, minutes.
Here I get R.
And then there are this, yeah, this is RT, this is RT.
Yeah, so
And
yeah.
yeah.
Right here.
So, but this is, it's, RT is R star.
RT. Ah, okay. So do you want me use the definition of these in terms of the
Mass ratio.
mass ratio? Okay. So I have.
Are you following?
So I use this one, right?
I'm trying to get this, I think, R star.
This one, and I plug in.
How do I get? Yeah, no, okay, no, that's fine. That's correct. Yes,
Okay.
that's correct. Okay, and you can. Okay, so this is the answer. Grazie. Okay, so alpha is. I like it to write it. So R star divided by square root of RT times RP, the geometric mean. Okay, so now you have alpha. Okay. Let me write it. Okay, so the answer is that alpha is R star divided by square root of RT RP. Okay, so someone getting closer to the first question? I'm happy with the first question. No? Okay, we'll go to, so someone can tell me what is this compression velocity per center? What is it? This compression velocity comes at the expense of the orbital energy of the star. The star is compressed within the plane and squeezed. So what is the component of the velocity that I want? This is the star is going in this direction towards pericenter. This is alpha. This is the velocity. Which component is going down and compress the star?
Sinus alpha.
Yes, what's your name? Again.
Oh, yes. Sorry, we're not very
No. Okay. How many tired? That's it? Okay.
I think there are
Two more?
Yeah. I think another one is missing today.
Okay.
In the conference of Itai's, we have a schedule.
Very good. Itai Aleph, Itai Bet.
Yes, I'm the second. I accept my state situation. Whatever.
Okay.
So this is alpha as well. So this is cosine.
This is a sign.
Because
No.
alpha. Sorry. Because if I do this,
So,
I have two parallel lines.
yeah. So this is his alpha, and this is his. So this is the velocity, and then which component of this velocity I want?
This one, no? Compression?
Yes. So Vc is equal. Can you write Vc equal?
Okay.
That's what I want.
Okay.
The
I'm not sure.
The Vc is the vertical component of the only velocity that is in the
velocity, which
in-
we have conservation of it. Yeah.
the,
I have no idea. I'm
the orbital velocity.
Yes, right.
Okay,
Right.
like Vp, for instance, because the pericenter, I think it's just half.
Oh, this is okay. Now it's
You see, the star is moving towards here, and then this is its.
very good. Thank you.
Okay, thank you. Okay, and so what is this? What is the orbital velocity for a parabolic orbit or for a Keplerian orbit? Someone else? I heard there was someone behind Itai, maybe an Itai echo. Okay, then Itai.
So the DM black hole over the pericenter distance.
Oh, okay, good enough. Good. So this is VC. Yeah.
Can you explain why do we care about theta and our sinus theta for this calculation?
Why couldn't we define alpha on the black hole?
With simply r star divided by r.
Well, if you okay, so this is here, right? Here where the star is as a size r star. Here it will be smaller, right? Here it's as the original size.
Okay.
And so I can define this is the plane. It's the same plane that goes through pericenter, right? It's the same plane. You see? You see?
Okay.
But here it's more convenient because I know the size of the star is r star. It hasn't been perturbed yet.
Okay.
Okay? So then I find alpha, and it's the same alpha that is here. So
What did you want to write in theta? R star divided by what?
By r Tidal.
le-
RT sine theta is much smaller than that if RT is smaller.
it's
than
smaller.
RT.
This is
You
it's
get
hi-
a different answer.
this is highly penetrating.
Okay, so I have two questions. I have one question on we have the plane perpendicular to this plane. I might be missing the geometry.
So I think just the drawing is misleading you because the answer is in the case that RT is much smaller than RT, but the drawing is
Yep.
not drawn in that.
Well, yeah, but RP is okay, smaller than RT.
Yeah, but only so it doesn't see the difference. Because
Oh,
it's not much smaller.
okay.
So if you would
Not
draw
on
something
scale.
which is much smaller, it will look like this. This will be the tidal radius. This will be the black hole. This will be the periapse distance. And in order to get so close, you'll have something like this. So this distance is much smaller than RT.
Okay. I see.
Okay. That's why you divide by this.
This
and not by RT.
but yeah.
And in the plane we were considering at pericenter, the relevant alpha will not be 0. Alpha is defined such that at pericenter, the relevant angle will
Yeah, that it's maximum. Yeah,
Okay.
that's right. Is that clear now? Is that okay? Okay. Okay. So we did this calculation and we got the answer. And then and this is the final answer. If you rearrange the term, that the compression energy is beta square, the binding energy of the star. So for grazing events, with beta is equal 1, beta is the tidal radius of the pericenter. So the compression energy can be neglected and doesn't enter into the spread of the star. But for beta, maybe 10, or much larger than 1, then it becomes important. This was, you find this calculation in Carte Luminé, which called this star that is compressed a crêpe stellaire, like a stellar pancake. Okay, so this is very nice. So we know how it compares with the binding energy of the star. And if I divide this compression energy with delta E that we derived before, this is the expression, and again, can be ignored unless beta is much greater than 1. But also, you see that it becomes important if the black hole mass is small. So for 10 to the 3, so la mass is intermediate mass black hole, then the nozzle shock is more important. We will see that, maybe. Okay, and in simulation that uses a small mass black hole, in fact, they see this effect. With 10 to the 6 and grazing, not important, 10 to the 3 and penetrating, then the compression energy becomes important. And then I asked by how much you would increase the temperature of the star. And then, you just take this energy per unit mass, you equate it to K Boltzmann times the temperature. and you obtain that the central temperature can be beta squared times the temperature of the star.
You're missing the mass of the particle on the left. M photon.
Oh, yeah, that's right. Yes, that's right. Okay. Then by hydrostatic equilibrium, or if you are taking a star in the main sequence, then its temperature, it's maybe 10 to the 6, 10 to the 7 to burn hydrogen. So if you have a beta greater than 3, then you can get a temperature which is more than 100 times, more than 10 to the 8 Kelvin, which is the ignition temperature for which burning reaction, which fusion reaction? Helium. Okay. So this has been worked out analytically, but computationally this squeezing has not been verified yet, but it's controversial. We don't know whether it's a numerical effect or not. What is for main sequence star? What is interesting is that for white dwarf, this compression and rise of energy occurs in degenerate matter. And you know that when like you hit a degenerate core, then you can have unstable ignition of helium, like the helium flash for low mass evolved stars. Okay. Sorry? Okay, so this is it. This will be a main sequence star. Yes. Okay, perfect. So you already done the calculation, so you will follow Svi better then. Okay. Okay, so we did. We work out the energy distribution here, the squeezing here. Okay, and then the stream goes on its journey, and now we'll do it together. We'll come back to a small exercise maybe. Can you draw the screen down? Yes, can you knock at the door? Ask. I will fix the typo of the mass, and then this slides will be available, I guess, right? If you want to redo the exercises and get the answers. Okay, so what I want to show you now, we're not going to calculate, but I want to show you. So this is a little break for you, and then another exercise is coming. Is how the stream evolve after the star is disrupted, before the second pericenter passage. Okay, so the length of the stream, this is determined by the spread in orbital energy that you have calculated. But what about the thickness? Okay, so not so good. Okay. So analytical argument and numerical simulation shows that when the stream goes out of its tidal radius, actually in the transverse direction, the stream is in hydrostatic equilibrium, which means that pressure balance self-gravity. And this confine the stream. And you can work out that the transverse direction is proportional to the linear density. And then L, you know, that is dictated by the difference in orbital energy of the streams. And this is just the result that I'm giving you, that when the streams at the beginning are still very close to the motion of the center of mass, you have that the transverse thickness increases r square root of r. A later time, maybe a few months later after disruption, you have so the streams are diverging more and more from are not close to the center of mass of the star anymore. And so you have the H goes as R to the 1/4. So the bottom line is that, what is that? Is H increasing, like it's getting, is the stream getting thicker or not? And how will you define getting thicker? How will you say, okay, now if H over R equal?
I mean, that would be the expectation.
Yes, so you say it's thick when H scale as, when H is about,
You mean proportional to R?
proportional to R, then you say that is thick. But you see that is, it evolves sublinear. So in fact, the streams, well, after they leave pericenter, they remain quite thin, confined. But there are some cases in which the density is in the stream may be not high enough for cell gravity to confine the stream. And then you have that indeed H goes as R. And these are, for instance, a few cases. So if energy, there is indeed like high penetrating events, they have energy injection for pericenter compression. Maybe the star is, it's pull apart and dispersed. And then you have that the transverse direction moves only under the tides. And you can work out, for instance, Sari et al. 2010, that H goes as R. Another case in which the density of the stream is too low for self-gravity to confine the stream is that the temperature in the stream drops below 10 to the 4 Kelvin. Then you have hydrogen recombination, which is injecting energy. And then you have, again, expansion. Okay. Hazen and Enrico. Okay. Are you ready? It's your turn again. So this is the last exercise you need to do. And then you need to, now we are here. So we have done the pericenter compression, the evolution of the streams, they remain thin, and now they are coming back. And I want you to derive correctly the famous T to the minus 5/3, assuming that this matter is moving ballistically again, so only under the gravity of the black hole. Remembering Kepler third law. And then think of a reason situation and also show that it depends on having the mass, equal amount of mass in bin of energy constant. And then think of reason why this shouldn't be the case. Okay, so let's say other 7 minutes. Your turn. Sorry, can you ask to read? So you want to derive the return rate of mass as a function of time. Hmm? Use the chain. And then use the Keplerian energy. Yeah. I did it badly. Okay. Do it rightly so you can move. Itai?
Yes.
Good?
Derive it. Just to take that. Oh, I need to. Okay, I have something.
Do you have something? You have something? Use the chain rule. Use the chain rule. The m over the t equal. So, like just a clue, you want to use what is called the chain law because you know how the energy and the period are related. They are moving on ellipses, right? Yes. And now I understand why you told me our star. Our star for me is the diameter of the star, not the radius. No, so
Oh,
why
okay.
did I ask?
So
Yeah.
if we use the chain
Yeah.
law and then we change, like we find the energy, the gravitational energy at the point, like on the elliptical.
Yeah. I want to show directly the m over the e. It should be there. The m over the okay.
Yeah,
Okay.
and then we assume it's a
The
constant,
m
right?
the over the t. Yes.
So our question is, when we write this, assuming we are on the elliptical radius of A, and we change to, like, we use Kepler's law to change to T. To this?
It's something missing. Yes.
Yeah. Okay, so what we're missing, that's what we wanted
There's
to ask.
something missing. Yes.
So this is like
Thinking-
the period, right? This
So
is
there's a relation between A and T. So you want to get to dA over dt
Yeah.
to use it. So dA over maybe dA over dt.
Why do we have to go through the differential expression?
Just because you want to use this.
But we could just replace it. I know it's why
Yeah,
isn't
yeah.
it correct to just replace it?
Just replace it.
Yeah, if we're saying that like it's proportional, everything is proportional. So just like change the A with the T to the
Yeah, but it's still something is missing. As is that you have T to 2/3. Think
but
just.
this is E and then we have to
Just
we have to
think
take-
think a little bit, okay? You have dE over dA. Just think a little bit. You're almost there.
I understand what you're saying.
Ah, okay.
I understand how we get
Ah,
there
okay.
if we do
Ah,
the
okay.
over dA.
Okay. So
What we're
what's
saying is that okay, we were bothered by something else, but now this is we still have to like to
Yeah,
differentiate this by
differentiate,
time, and then we
yes.
get the correct.
yes?
Okay, no, so okay,
Ah,
so,
okay.
so we didn't
Yeah, I
have
thought that you did not because I didn't see that you differentiate.
no, we
Yes, yes.
differentiated, but the question is, this is the period, right? This
Yes.
is like a proportional
Yes.
period of the elliptical. Is it the same time of the m, like this
Yes.
the m and the t
Yes.
is the same
Yes.
time? That's what
Yes. Yes. It's the same time. So it's the return. This is dt. Is basically the period.
that was
Yes.
what
Ah,
was-
okay. Then it's okay. Still the compression. Still the compression.
Yeah, yeah.
You don't like the compression.
Yeah, this is easy, but the compression is.
The compression. Okay. Okay, who has finished? Who has the answer? You have the answer? Yes. Okay. So I think I'll stop here because I have a girl coming over. What's your name? Tiara. Tiara. Oh, that's right. Hi, Tiara. Sorry, I know her. Sorry, I'm terrible with.
Okay. So basically, if you use a chain rule, this becomes the end times T. And we know that orbital energy is like this. And then if you plug in the Kepler's law, A will be proportional to this. So if you do like the
Right.
T, that will be proportional to T to the minus 5/3, but that depends on this proportional to a constant.
Yeah.
Yep.
Yes. Great. Thank you. Yep. Thank Tiara. Okay. So that was the famous calculation and why we are obsessed with t to the minus 5/3. This is being constant. What does it mean being constant? It means that we have a distribution which is actually, let me do this like this, which is like top hat. And this is 0, and this is minus delta E, and this is plus delta E, right? Okay. And this is the dm over dE, so the amount of mass in every beam of E. So why it's is not completely realistic? This is the amount of mass in each beam of dE. Yes? The stellar, not composition, but density. Yes. What's your name? Tarane. Okay. Yes. So this corresponds to which part of the star? Yeah. So again, this is my black hole. This is the star. Minus delta E, visually, which part of the star may be placed? The leftmost, so here. Is there the same amount of mass here or here? So here corresponds, this is its minus delta E, and this is 0. So flat means you have equal amount of mass in each delta R. Okay. Instead, what your name again? Tarane rightly so said. Okay. Yes. First of all, it's spherical, but there is also a gradient of density, right? The density increases towards the center. Okay. So what you can calculate, can you see it? You can take a different model for the star, different polytrope, for instance, and you calculate dm over dE as a function of E. And then you go back to the expression of the that you derived of the fallback time, and what you see. What's different from the calculation you made? What's the effect of having less mass of, sorry, less mass here than here in the same bin of the DE? Yes, but so what the consequence for the m over dt, the mass return fallback rate? So this is what you just calculated, which comes from this part here, which is flat indeed, the least bound. Right? Is the least bound. Is the one that Itai told us it has zero, almost zero energy. And indeed, there is the distribution is flat, and we have the t to the minus 5/3. But what this causes, this modulation? I heard, yeah, Manuele?
Less mass at the very bound mass is less, and so this is the mass which falls back earlier.
Yes.
And so you have less luminosity in the beginning.
Yes. So
You deviate down from the
yes.
straight line that you have.
Yes. So we have a rising. You know, the idealized case is just a straight line. But instead, the fact you have less mass, but it's increasing towards this flat part, means that we have a rising. And the idea here is that if this is also how the flare behaves, the idea is that if we can catch this rising, we can tell what is the star composition, because the peak depends on the density distribution within the star, and different type of stars associated with different density distributions. Okay, so this is the catch. We want to catch it, catch the flare early enough to see the rise, so that we can get a clue on which kind of star get disrupted. Okay, and how much time do I have? 15 minutes, right? Ah, okay. What was it? Okay. Okay, so we'll do this together now, and okay. Now you can rest your pen, but not your brain. I need you. Can you draw back the screen, please? Ben, can you ask, please? Sorry. A coffee on me afterwards. Okay, and now we have this material coming back, and I want this material to form a disk, to circularize. And we're going to do the calculation together. What does it mean circularize? That this highly eccentric stream, right, you used ellipses, Tara, to calculate the return rate, and we want these ellipses to form eventually a disk, so be on a circular orbit. Okay, so the simple way to think about it is that the debris had a spreading orbital energy, but they have more or less the same angular momentum of the star, of the parent star, which is this one. Okay? But then we know we want these streams to circularize, and since they have the same angular momentum, they will go through the same pericenter. That's why the compression. So we want them all to circularize at this radius, which corresponds to this angular momentum. Replace the lamp. Okay. Here there is a footnote that says that that you cannot see, but you see there. Ah, okay. Okay. That V for an elliptical orbit it differs from the velocity, orbital velocity for a circular orbit by square root of 2. And so I get the circularization radius, which is the famous 2 times the pericenter I was mentioning yesterday. Okay, now question for you. So this is where I want to circularize. But I have a very eccentric stream. So I want the semi-major axis to shrink, right? So I want to lose energy, orbital energy. So what is the energy I need to get rid of? Or how would you calculate it? You have an ellipsis, so you want to go to a circle. You have the energy of the whisper. So I would say initial orbital energy minus the final orbital energy. This is the amount of energy you want to get rid of. Okay? So, and this is the result. I said, well, should be strange. This is the result. What is this? What is this? This is the final energy. So why I'm saying this is actually the energy you need to get rid of?
Because it dominates if you start from the...
Because in fact, when you take, so you should start from the total binding energy of the stream minus this. But if you take the ratio, you see that the circularization energy, the initial orbital energy of the stream that you calculated divided by the circularization energy is b to the minus 1, this mass ratio to the minus 1/3. You plug in the usual numbers and you get 1%. Okay? So this tells you that if you take this energy and you radiate away to get rid of it, then you can circularize your stream at 2 rp. But if somehow 1% of this energy remain trapped in the flow as you try to circularize, you unbind the whole thing. So it's a tricky business, circularization. And so that's why we think that outflows are involved. And this, I think, Svijo will talk about it. Yeah, so he has opinion, so that's good. And I'll let him... being efficient in the standard picture, it means that it's circularized at this time scale. And that's it. Right? That's it.